So let's do one of our problems here. Suppose we're given a vector u. It's a two-dimensional vector, has 2, -1, and we have a vector v, another vector, 4, 5. Find, if possible, a new vector w, so that the projection of w onto u is just u, and the projection of w onto v is just v. So somehow we say, look, we're looking for a new vector so that from the perspective of u, it looks a lot like u. And from the perspective of v, it looks a lot like v, but of course u and v are very different types of vectors. So how can we do this? Well, so what's true? Well, we're looking for a new vector w. So w is going to be two-dimensional. So I don't know what it is yet, but I do know I could write whatever the answer is as two entries, a, b. All right. Well, what needs to be true? If we think about the projection formula, the projection of u onto w, the formula for that is you're going to take w dot u and divide it by u dot u, and then you're going to multiply that by the vector u. And similarly, over here, same process. The only thing is that your u's are going to become v's. So, what needs to be true? Well, what needs to be true, say in our first case, if I want to end up with u, the part that's in front had better be equal to 1. All right. So really, what do we need? Well, we're looking for some w which has the following property, such that when I take w dot the vector u, that's equal to u dot u. And when I take w dot the vector v, that's equal to v dot v. So if that's true, then our projection works. All our requirements work out. So we're translating our requirements into a series of equations. And now we can go one step further and say, okay, well, let's write out what this actually means. Because here I have a dot product, w, and I have u. So w dot u would become 2a minus b. Well, that's got to equal u dot u. Well, that would be 2 times 2 plus -1 times -1. That's 4 plus 1. That's equal to 5. Then w dot v, well, that would be 4a plus 5b. That's got to equal v dot v, 4 squared and 5 squared. So that's 16 plus 25, making 41. And now we're back into our classic 2 equations, 2 unknowns. And you're probably thinking, math seems a little bit repetitive. We keep coming back to these 2 equations and 2 unknowns. It's a very common thing to do. Essentially, we said, look, we'll start out very young. We'll have 1 equation and 1 unknown. And now we're up to 2 equations, 2 unknowns. And you're thinking, all right, when I hit graduate school, I know what's going to happen. 3 equations and 3 unknowns. No, that's going to come a lot sooner than you think. But, all right. Well, at this point, we kind of know what to do. So, for example, if I multiply the first equation by 5, with an I to cancel the b's here. See, if I multiply it by 5, that would say 10a minus 5b equals 25. I still have 4a plus 5b equals 41. And if I add these 2 equations up, 14a, the b's cancel, is equal to 66. So a, just a, is 66 over 14, also known as 33/7. All right, so you get a, 33 over 7. Woohoo! Now you might think, wow, that's an unusually not nice number for your type of problem, Steve. But you know what? That's one of the things we learned. Look, we don't have to have nice numbers all the time. The other thing I could do is I can multiply the first equation by -2. That would give -4a plus 2b over equals 5, excuse me. Why did I say over? 4a plus 5b equals 40. Oh my gosh, I can't multiply. That's -10, not 5. Okay, multiply first equation by -2 with an I to cancel the a's. And now if you combine, the a's cancel, 7b equals 31, and so b equals 31 sevenths. So there's our answer. A should be 33 sevenths, and b should be 31 sevenths. Just like we would have thought when we started. Well, maybe not. All right. Now, that's, of course, the algebra. Could this problem have been done purely geometrically? Well, in a sense, yes. So let's think about it. Suppose I have a vector u. Let's say, I see x is positive, y is negative, so it's going down. Let's say this is what u looks like. So here's my vector u. And now I ask the question, what's true about vectors which would project onto you? And let's suppose, for right now, that they all have the common starting point. Well, if I'm going to project onto you, what has to be true? See, if I don't go very far, say I only go a little bit, if I try to project onto you, I'm too short. If I go too far and I project onto you, I'm going to miss. See, I have to be in that sweet spot, that sort of Goldilocks zone, where when I project onto you, I'm going to be just right. So where is that? Well, imagine coming to the end of u and drawing that perpendicular line. So any vector which starts here and goes and stops at that perpendicular line, when I drop straight down to u, that would produce the vector u. It's a true statement. Any vector that has that, in fact, all vectors that have that property are going to project onto u. Again, I have to start here and go to anywhere on that line. Now that's u. What about v? Well, what does v do? Well, v goes out as 4, 5. Well, let's say this is v. Well, now what has to be true here? Well, same argument. You've got to be perpendicular to this segment, wherever it ends. And I did not plan well, but what am I looking for? Well, I've got to be on that line if I want to project onto you. Got to be on that line if I want to project onto v in the right way. So our vector would be wherever those two intersected. So there's a geometrical intuition that you can do, so that should the algebra ever fail you, it never will, but should it, there's always geometry to fall back on. All right. So let's move on to today's topic. Now for today, we're going to continue our discussion of vector products. And we've already talked about 2 of them, and you might think that 2 sounds like too many, but let me remind you what they are. The first product is what's called the scalar product. Now the scalar product says you take a number, you multiply it by a vector, you get a new vector. And in this case, the scalar product is just saying, let's lengthen that vector, or maybe we shorten it, and occasionally we might flip it around. All right. And this can make unit vectors. The one we talked about last time is the dot product. Now dot product says take vector dot vector, get out a number. And what is that number? Well, it has a geometrical meaning. In particular, u dot v is the magnitude of u, magnitude of v, cosine theta. So we see that theta, what is theta? It's that angle between the vectors. So if you were to draw a picture here, which we probably should, so if you have vector u and a vector v, theta is the angle if you were to put the tails together. So you can find that angle. You can also see whether or not 2 things are at a right angle, because cosine of 90 degrees or cosine of pi halves is 0. So you can find orthogonality or test it. And we can do projection. So now we're going to talk about our last product. It's the cross product. And the cross product, this is the one that says, this is what really should be happening. A vector and a vector gives a vector. Now, our notation for a cross product is you put a little bit of a tiny cross, and hence the name cross product. So it's easy to recognize what type of product that we're talking about, because notationally we distinguish all of them. Now, there's a caveat about the cross product. See, the cross product only works in dimension 3. Now, very conveniently, we live in dimension 3. You know, you got to feel bad for those aliens that live in dimension 17. and they're like, they're sitting in their class, and their teacher says, there's this fun thing that works in dimension 3, and they're like, yeah, but we live in dimension 17. It's not very useful. But for us, it's really useful because it's the right dimension. Now, you might be thinking, why 3? What's special about 3? And it turns out that 3 has this really cool property, and it's the following fact. 3 is the only number that satisfies the following. It's equal to 2 plus 1. And that's why it only works in dimension 3. Now, you might think that's overly simplistic, but that's actually what it boils down to. So when I talk about the 2, those are the 2 vectors that we start with, the vectors that we're putting into the cross product. And when I talk about the 1, that's the vector that comes out. So that's why we need to put 3, because we need to have just enough. Okay, so let's talk about why. What's going on? Well, if I ever want to talk about a vector, I always say, look, a vector has 2 important properties. It has direction and it has magnitude. So let's talk about the direction. And this is why we're talking about that dimension 2 plus 1 equals 3. Because here's what happens. Suppose I have 2 vectors. Well, if I have 2 vectors, I can think about the 2 vectors are contained inside of a 2-dimensional subspace of 3-dimensional space. So in particular here, what I have is say, here's a vector u, and here's a vector v. And they're both inside of this plane here. Now, the nice thing is, I have to say, I have to come up with a nice, consistent rule about my direction for my new vector. If I have a plane in 3-dimensional space, and I want to say, what's a nice, consistent direction that I can say is well-defined? And the answer is, it's the direction that's perpendicular to the plane. So that's, the plane is the 2. That perpendicular direction, that's our new direction. That's our plus 1. However, we still have a small challenge. We can say, look, I could be perpendicular to the plane in 2 ways, because I could be coming up from the plane in a sort of a quote-unquote positive direction, or down from the plane in a quote-unquote negative direction. So I do have to make a decision. Essentially, it says, like, I have this sort of symmetry going on, and I have to break the symmetry. So how do we do it? Well, if you've ever heard of the right-hand rule, this is your chance to shine. Because it turns out, if you've ever looked at your hands, you'll see they're actually not the same. They have symmetry, And so we break it and say, okay, so we're going to use our right hand. So how does it work? So you notice that your hand has this sort of bendy, hingy part right here. And so that bendy, hingy part is going to be helpful. So you're going to put U on your fingers. You're going to put V on the palm. And then the thumb points in a certain way. And it points up. And so here, for instance, we would have, imagine I could draw a hand. So you have your fingers coming up here. This is your U. The palm of your hand on your V. And here's your thumb pointing up. Okay. This is, I probably should take some art classes at some point. All right. It looks more like a turkey than a hand right now. But this is the philosophy. And notice that essentially what has to happen is that the angle, it's going to be the acute angle that goes between, because unless you have something very seriously wrong with your hand, it doesn't go this way. So it does make a decision. Now, you might start to get nervous. How much do I need to know about the right-hand rule for this class? And the answer is, I don't think we've ever done anything using the right-hand rule. But it's just in case, you're trying to decide 100% certainty, what happens, then you have it. You have that. Okay, good. So that's our direction. Now here's the thing. This is like super, super important, because this fact right here, the fact that U and V is both perpendicular to U and V, that is going to be our like main tool for when we use this rule. Again and again, we're going to say, oh man, if only we could find something that was perpendicular to 2 vectors. And then it's going to be like, aha! something has crossed our mind. The cross product, that will be our tool. So it's really good to have it. Now that's not enough, of course, to do a vector. We need one more piece of information. In addition to direction, what else do you need? Magnitude, right, good. So what is the magnitude? And here's the rule. So the magnitude of u cross v is the magnitude of v sine of theta. It's a little bit like the dot product. You saw that there was the cosine theta, magnitude of v cosine theta. Here it's magnitude of u, magnitude of v sine theta. All right, so the other thing that we wanted to do is we wanted to be a little bit reasonable. And so here's our little bit reasonable. It should be able to distribute. So in other words, we want to be able to expand. Which is to say that if I take u plus v cross w, I can distribute in. So that's u cross w and v cross w. Or if I take w cross u plus v, again, I can distribute in. So that's w cross u plus w cross v. These facts here are enough for us to completely determine what the cross product will be. And they're all fairly reasonable. Maybe. Maybe. All right. So here we go. Let's start talking about how lovely and reasonable things are. So we'll start with some really basic facts. Here's the one that really sort of like makes us think maybe it's not necessarily the coolest thing ever. And that is that it matters the order that you take the product. So u cross v and v cross u are no longer the same. Now what does that mean? Well, it means if you change the order of multiplication, there's a negation. Now, that might seem a little bit strange, but now just think about where negation is. Really, when you see a negative here, it's about orientation. And so when you see that negative sign coming in, it's like, oh, an orientation has flipped. And so if you think about what's happening, it comes back to that right-hand rule. So if you have u cross v, if you want to do v cross u, you have to turn your hand over to get your hand to fit. So it's that turning that hand over, you're changing your orientation. That's where the negation comes in. All right. The other thing that seems very non-intuitive is u cross u is going to be 0. So if I take something and I multiply it by itself, I'm going to get 0 out. Now how can we see that? Well, for that, you can look at the magnitude formula. See the magnitude formula down here. The magnitude of a vector cross a vector is the magnitude of u times the magnitude of v times the angle, sine of the angle of in between. Well, what's the angle between a vector and itself? It's 0. Sine of 0 is 0. And it's really hard to recover from multiplication by 0. So if I have two vectors that are parallel to each other, so anytime two vectors are parallel, their cross product will be 0. Well, I should say the magnitude is going to be 0, but there's only one vector that has magnitude of 0, and that's the 0 vector. All right. Once you can believe those two things, then it starts to make sense in what follows. Let's start with our nice basic vectors here. And as a recall, we have, these are the vectors I, j, and k. So I points in the positive x direction, j points in the positive y direction, k points in the positive z direction. Now there's a couple of nice things about these vectors. One nice thing about these vectors is that they're all perpendicular to each other. So in other words, if you look at the angles that you're forming here, they are all right angles. So you have a nice set of right angles to work with. So that sine of the angle in between is always going to be 1. These vectors, I, j, and k, all have length 1. And so the cross products that we have to figure out all have length 1. So that's pretty good. So in the end of the day, if we're finding a vector which has length 1, we just have to figure out the direction. So suppose you have I cross j. Well, again, you can start using your right-hand rule. So x direction, y direction, where are you pointing up? Which direction? Yeah, you're pointing up in the direction of k. So that says I cross j is k. Well, now, no work, we get that for free. J cross I, you just flip the sign, negative k. All right, j cross k. So you got to like contort your hand. Where are you pointing? So fingers on j, palm on k, you point. You're pointing in the I direction. All right, so again, k cross j, that's a freebie, negative I. All right, rounding the corner, k cross I. So you got your fingers on k, your palm on I, and we point how? We point j. And so then I cross k is negative j. Now, okay, that's all nice. But how do we get a formula for just a generic vector? Because these are like really special vectors. We want to be able to like handle non-special vectors. So something like ABC cross DEF. Can we handle that? And now we can. So just one thing to recall, we do have our distributive property. And we're going to use that for what's about to happen. So here we go. Exciting times. So that ABC cross DEF is another way to say AI plus B times J plus CK plus DI plus EJ plus F times K. Distribute. And if you distribute, okay, you're going to get a lot of terms. Now, you might think, wait, I thought FOIL only had like 4 terms because that's part of FOIL. But the reason you're going to get a lot of terms is the philosophy of FOIL just says for every single expression in the first part, and there's 3 different ones, and for everyone in the second part, there's 3 different ones, you pair them up in all possible ways. So that gives you 9 possibilities. So it's no longer FOIL, it's probably something because there's like 9 things you have to do. So, but that's really hard to remember, so we just say you FOIL. All right. So if you multiply it all out, for example, here you get the A, I plus E, J. So that's A, E, I cross J. You expand all that out, you get to a point where you say, lo and behold, you get a lot of these things like, J cross I and I cross K. And now we start saying, aha, there's a lot of cool stuff that happens. In fact, a lot of great stuff happens. What happens? Well, anything that's a vector cross itself, so these I cross I's, J cross J's, and K cross K's, they all go away. These other terms, things like I cross J, well, that becomes K. I cross K, well, that's negative J. And so we can replace every one of these 9 terms with just either 0 or a new direction. And if you do that, this is the result. You get AE times K minus AF times J minus BD times K and BF times I and CD times J minus CE times I. Or if you put it back into component form, you get in the first entry BF minus CE. The second entry is CD minus A times F. And the last entry, AE minus B times D. And you're probably thinking, just what we thought it would be. Probably not. But all right. So how do you remember that? Well, the good news is you don't actually have to remember that. What you need to do is get to the place where you can say, hey, let me find a process to figure it out. So there's actually a nice process. So we're going to take a little bit of a detour here, but it's going to be a short detour. So we're going to talk about determinants. So what's a determinant? So suppose you have something called a matrix, and you can think of a matrix for our purposes as it's an array of numbers. And a determinant says, I want to come up with a special value that's associated with this array. And so what is it? Well, if it's a 2 by 2, that special value is called the determinant AD minus B times C. All right. So that's what it is. Hopefully you've seen this before. What if it's 3 by 3? All right, well now it gets a little bit more, well, I wouldn't say exciting, but there's a little bit more to do. Now it turns out that for 3 by 3 there's a couple ways to handle the determinant. Now here's how I like to do it. I either write this down, or at least I'm thinking about it this way, is I take that 3 by 3 and I copy the first two columns over at the end. So you can see I still have A, B, C, but then the first two entries again, A, B, D, E, F, and then the second two again, D, E, or G, H, I, and then the last two again, G, H, first two again, G, H. Now if you think about what happened here, you notice that you went AD going down, then you subtracted BC going up. We're going to do the same thing. So we're going to go down, and if we go down, we're going to get A, E, I. Then the next will be B, F, and G. And then the last one will be C, D, and H. So going down, add. Now switch directions and also switch signs. Going up, GEC, subtract, GEC. Is that? Yeah, that's kind of readable. Going up, HFA, so subtract, HFA. And finally, going up, subtract I, D, and B. Okay, so write the first two columns over. Now take your 3 by 3, put the first two columns. You add, and you subtract. And that's a quantity. It's a number associated with your matrix. By the way, this number is really cool. There's this beautiful class that hopefully you're all going to take about matrices and linear algebra and all these fun things. It's a great subject. Now that's one method, and I say it's 3 by 3 special in that because essentially it stops working after this case. 4 by 4 won't work. But there's another method called the cofactor expansion. And the idea of cofactor expansion is you do the following. You go along a row. Now, in our case, we usually go along the first row and say, okay, for each entry, we take that entry, and then that's A, and then we cross out the row and the column that it's in. And what's left is a little 2 by 2, E, F, H, I. Now take the determinant of that 2 by 2. Then go to your next entry, B. Cross out that row, that column. You're left with a little 2 by 2, D, G, F, I. Then go to your last entry, C. Cross out that row, that column. You're left with a little bit of a 2 by 2. And the key here to remember is you alternate sign, plus, minus, plus. If you go through and you multiply this out, well, we have time. So you would have A, I'll put it up here since there's space, times 2 by 2 determinant, EI minus FH, then minus B, DI minus FG, and plus C, DH minus EG. And if you check, here you're going to get A times E times I, which matches there. Over here, that minus B times minus FG will become B times F times G, which matches there. And on the end, you get that C times D times H, which matches. And now you get a minus C times E times G. That matches this term here. So minus C times E times G. You get a minus A times F times H. So that matches. And finally, you get a minus B times D times I. And that matches. So both these give the same thing. Now, why are we talking about these determinants? Because they're very, very useful. So, here's the fun fact. If I want to find the cross product of two vectors A, B, C, and D, E, F, I can do it by determinant. So I'm going to take the determinant of a 3 by 3 matrix, and in the first row are the directions I, J, and K. The second row is the first vector, A, B, C. And the last row is the second vector, D, E, F. And if you multiply all that out, do the work, lo and behold, you're going to get the determinant. You're going to get the cross product. It works. It works. Okay. So let's find the cross product of two vectors. All right. So we need a first vector. What's our first vector going to be? Negative 1, 5, 4. What's our second vector going to be? What? 3, 3, 3. All right, that's a vector. Okay. Negative 1, 5, 4, cross 3, 3, 3. So, I, J, K, negative 1, 5, 4, 3, 3, 3. Again, I like to write it out, at least the first few times. Oftentimes, after you do this a few times, you say, I don't need to write it out. I'll just remember to wrap around. So, wrap around. As you go down, need to wrap around. So, we get I, 5, 3 would give us 15I. J, 4, 3, 12J. K, negative 1, 3, negative 3K. So I went down. Now I'm going to go up. All right, 3, 5K. What would that be?
Negative 15.
Yeah, so it's 15K if we multiply, but because we're going in that opposite direction, we subtract. Negative 15K. 3, 4I. Negative 12I. All right. 3, negative 1J. Yeah, positive 3J. So, 15 minus 12 gives 3. 12 plus 3 gives 15. And minus 3 minus 15 gives minus 18. Good. Good. All right. Let's see. What's this next one? All right. Now, verify it. Okay. So what do we mean by verify? So this is one of the things we want to do. We want to get to the point where we say, okay, I can do some work, but is there a way for me to check my work? Now, one way to check your work is, let me do it again. There's a downside in that it might take a long time to check your work by doing it again. And if you made a mistake once, you might make that same mistake again. So you'd like to have a way to check something that's short to do and involves a different type of computation. So what's a way to check? Well, there's a hint here, and it says, hint, u dot u cross v should equal 0, and v dot u cross v should equal 0. Why is that true? Yeah, cross product has a special property. It's one of the most important things about cross product. The cross product has to be perpendicular, or you might hear the word normal often used, to what you start with. So we started with u and v, so the vector that came out has to be perpendicular to what came in. So how do you tell if two things are perpendicular? The dot product. So the dot product can help us check our cross product work. So, as an example, let's say negative 1, 5, 4. We'll dot that. 3, 15, negative 18. All right. Well, we multiply these out. Negative 1 times 3. Negative 3. 5 times 15. 75. 4 times negative 18. It's negative 72. All right. Negative 3 plus 75 minus 72 is 0. Now, 3, 3, 3. That's our other vector. Dot 3, 15, negative 18. All right. 3 times 3? 9. 3 times 15? 45. 3 times negative 18? It's negative 54. 9 plus 45 minus 54 will give us 0. Now, is this a guarantee that what we did was correct? No. But if it works, it would be amazing if it was somehow we made a mistake. Usually 99.99% of the time that this works, you did it right. And even in that other 0.01% of the time, it probably doesn't matter. Because one of the things we most care about for cross product is direction. Something perpendicular to what we started with. And then, lo and behold, that gives us our direction. Now, of course, you're probably thinking, but Steve, there's got to be something we can do about that magnitude. It's got to be useful. All right. So let's talk about magnitude. So, like I said, the main use for the cross product is we have two vectors. We want to find a new vector perpendicular to the ones we started with. But the magnitude has meaning. And especially because we see that sine theta floating in, we're going to think, okay, maybe we can think about what that means. So we're going to start thinking about geometrically what's going on. So here's our basic picture. Suppose we start with two vectors, u and v. And we put the tails together. Now one of the things that you can do is you can actually put another copies of u and v on the other sides. And if you do that, you form this nice shape here called a parallelogram. You say, all right, well, what can we do with that? Well, suppose our goal here is we want to find the height. And, well, I gave away what the answer is. Okay. Let's find the height of this parallelogram. So how do you find the height? Well, if it was a rectangle, it's really easy to find height of a rectangle. What's the height of a rectangle? Base times height. In fact, for parallelograms, it's the same thing. It's base times height. The problem is, what's the height? Well, the height would be if you drop straight down. So imagine we drop straight down. The base, I can take that to be the length of the side down here. So let's look at this triangle. Of course, it's not just any kind of triangle. What kind of triangle is it? It's a right triangle. So we have trigonometry. Do we know the length of any side? We know the length of the hypotenuse. We don't know the length of this side because I don't know where it's going to land when I drop down. But I do know the length of the hypotenuse. So I have the length of the hypotenuse. I have an angle, theta. I want to know the length of the opposite side. So what relates the opposite side and the hypotenuse in a right triangle? Sine. And in particular, the length of the opposite side is the length of the hypotenuse times the sine of theta. So this is your height. The magnitude of u is your base. So the area is going to be base times height, magnitude of u times magnitude of v sine theta. Well, magnitude of u, magnitude of v sine theta, that is the magnitude of the cross product. That's the magnitude of u cross v. So now we say, okay, that's really beautiful. Now one of the things that throws people off is they're like, but wait a second, how is it that a length is equal to an area? Because u cross v is a vector, and when I talk about the magnitude of u cross v, that's equal to the length of something. But here I'm talking about an area of a parallelogram. And it's not that necessarily the length is the vector, it's that the measurement of the length is equal to the measurement of the area. They have the same value. All right. Now you're probably thinking, well, that's great, but I may not want to really care much about parallelograms. My passion is triangles. I love triangles. So suppose now I want to find the area, not of the parallelogram, I want to find the area of a triangle. Well, what can you do? Yeah. So the area of the triangle, that's half the area of a parallelogram. And therefore, the area of a triangle is half of u cross v. So that's great. Triangles, that's our bread and butter. They're nice. They have wonderful properties. Okay, so let's do a quick example. Find the area of the triangle with vertices. All right. I need some vertices. These are three-dimensional points. Okay, so you're going to be nice to me. I appreciate that. Thank you very much. All right. I need another vertex. 1, 1, 7. And one more. 2, 4, 8. Okay. Now, what's going on? Well, what's going on is I have 3 points in three-dimensional space, and we'll just mark them off. Here we go. And there are 3 points. Now, you might say, I don't think that was drawn accurately. For instance, I don't think 0, 0, 0 was marked correctly, even though I haven't told you which one was 0, 0, 0. That's okay. We're trying to get intuition. Pictures don't always have to be precise to be useful. So this is 0, 0, 0. Here's 1, 1, 7. And here's 2, 4, 8. And now I have a triangle. And I'm trying to find the area of this triangle. So if we want to use our formula, which we probably want to do, because that's about the only thing we have going for us right now, we need vectors. Right now, we don't have vectors. We just have a bunch of points. So what's our next step? Find vectors. Now, the question is, which vectors? Because you actually have an amazing amount of choice. There are 6 possible vectors that could come into play. Because you have 3 points, you can pick any pair of points, and once you pick any pair of points, you can go in either direction. So the question is, does it really matter? The answer is to a small degree, but ultimately, there's lots of ways to do it. Because I have 0, 0, 0, it's a very nice one to work with. Let's anchor ourselves here, and now let's make the vectors on these 2 sides. Because those are pretty easy vectors to find. When in doubt, pick the easy way out. So the vector from 0, 0, 0 to 2, 4, 8, what is that vector? It's 2, 4, 8. The vector from 0, 0, 0 to 1, 1, 7, what is that vector? 1, 1, 7. So now I have 2 vectors, and the important thing is that they come together in the right way. So in other words, there's this angle theta here, as it should be. All right. Well, how do we finish? The answer is we take the cross product, take the magnitude of that, and divide by 1/2. So let's take the cross product. So we'd have I, J, K, 2, 4, 8, 1, 1, 7. And here, I'm going to wrap around. You know, we're advancing quickly. Okay, so I times 4 times 7 gives 28I. J, that's the J. J times 8, wrap around to 1, gives us 8J. K times 2 times 1 gives us K, wrap around, 2 times 1. K times 2 times 1 is 2K. 2K or not 2K? That is the question. It is 2K. I times 4 times K? Yeah, minus 4K because of the way we're going. I'm just going to put that underneath the K. 1 times 8, wrap around to I. Negative 8I. And 7 times 2 times J. Negative 14J. And if we put that together, 28 subtract 8, that's going to give us 20. 8 subtract 14, that gives us negative 6. 2 subtract 4 gives us negative 2. All right, now, if we were worried, what would we do next? Yeah, just do a quick dot product. Okay. Yep, that works. Okay, good. You probably should do it a little bit slower, but yeah, it works. It works. 40 minus 24 minus 16, that's 0. 20 minus 6 minus 14, that's 0. Life is good. Life is good. All right, we're not done. What comes next? Magnitude, don't forget, and then divide by 2. Or actually, you can do both, because the nice thing about magnitude is you can put the half inside first, or you can do it later. So it doesn't really matter. Do you want to do the half first and take magnitude, or take magnitude and then multiply by half? Same answer. Here's my notice. Everything's divisible by 2. So might as well take a half first to make the number smaller. Okay, so if we divide by 2, so we'd get 10, -3, -1. Take the magnitude there. All right, square root of 100 plus 9 plus 1 gives the square root of 110, which you can also write as the square root of 110. Yeah. Well, it doesn't really simplify in a nice way. Okay. All right. Well, there you go. There you go. Now, here's another question. So suppose we change it up. And to help speed up here, find the area of the triangle. Well, you have 1, 3, 2, -1, and -4, and -3. Okay, so suppose you wanted to find the area of the triangle with those vertices. What do we do? Okay, now, what do we want to do? We want to find vectors, take the cross product, and say like, oh, this is so easy. But why can't we do that? It's 2D. What do you need to have cross product? 3D. So the cross product doesn't work. But somebody said, what if we said make the last part 0? Ah, see, this is the cool idea. It says, hey, if you've got something that works great in 3D, you can also make it work for 2D, because, fun fact, 2D is smaller than 3D. A two-dimensional thing lives inside of a three-dimensional thing. So the key here is you add in zeros on the end. So 1, 3, 0, 2, -1, 0, and -4, -3, 0. And then you keep going as we did before. Okay, so let's talk about one more thing. So we've talked about a parallelogram, two-dimensional. Let's do the three-dimensional. Parallelepiped. So it's a three-dimensional box, but we've tilted, we've tilted our things. Just like a parallelogram, it's like a tilted rectangle. Now, if you think about what's happening here, you can say, well, really what's happening is instead of just two vectors, so for example, u and w would be two vectors, would form a parallelogram, now there's three. U, W, and V. And you say, okay, so the three vectors form the three sides. And of course, you translate. So there's 4 copies of U, there's 4 copies of V, and there's 4 copies of W. And that forms our shape. Now, it's a pretty flat thing, and we like to say, well, what's the volume? How much volume does this thing have? So we can answer this to a degree. So in particular, what we're going to do is we're going to say, well, what's the volume of a box? If you think about a three-dimensional box, you get that the volume is the base of the box and then the height of the box. Now in our case, we have this part down here shaded in a little bit, and so that shaded part, that's our base. So here's our base. And then we also, notice we have this dotted line. That says come from this point and drop straight down. So this is our height, h. Now one thing to note is really if you pick any point upstairs in this top parallelogram and were to drop straight down to the floor that contains this parallelogram, then you'd always get the same height. And so there you go. Okay, so now what do we have? Well, volume is base times height. Well, what's the base? Well, the base That's a parallelogram that involves the vectors u and v. We know how to find the area of a base. We've done that. And therefore, we have that the volume, which is base times height, is this cross product, magnitude, times height. Now, what's left? Well, we've got to figure out the height. Okay, so here we go. Suppose for a second that we look at an angle. So let's think about what's happening here. I have this base here, which comes from u and v, and we take the cross product, and we can get a perpendicular direction. Now, why do we take the cross product? Well, because I want to have something perpendicular. See, this is a perpendicular line segment. So what's true is if I think about this vector, u cross v, it's sticking up. It's not the right length, but it has the right direction. So there's this vector u cross v sticking out somewhere. And I can look at the angle that's happening between the vector w and the vector u cross v. So there's this theta. Now, what's special about this? Well, if we think about what we're after the height. So if I knew this angle theta, which is the angle between the vector w and the vector u cross v, and I knew the length of w, then I'd say, oh wait, there's this right triangle here. So I know the length of the hypotenuse, I want the length of the adjacent side, and I have the angle theta that's in between these two sides. And what it would be is you would take the length of w times cosine theta, that would be h. So it would be the length of w times cosine theta. Now, one small catch, tiny caveat. It's not quite true. You'll notice we're going to add just a little bit more. And that is because it's possible that theta was an obtuse angle, and so that cosine theta was negative. Well, that just means we picked the wrong choice for theta. In that case, we flip the acute angle, but all that needs to be done is make the sign positive, which means take an absolute value. All right, so here we go. Let's put this in. What do we have? Well, we now have the magnitude of u cross v, the magnitude of w, and cosine theta, because we have that magnitude of u cross v and the magnitude of w times cosine theta, base height. And I can move this into the absolute value. And now if we stare at this a little bit, we see, it's a magnitude, and an angle between. Well, when you see magnitude, angle between, that's the dot product. So it's the dot product of our vector w with u cross v, whatever that turns out to be, then take the absolute value. So there's the volume. All right. Now here's an amazing fact, really, really beautiful fact. Suppose I wanted to find w dot u cross v. How do I do it? And the answer is you just make your matrix of these vectors. So the first row is w, the second row is u, third row is v. And you take that determinant. And now, what does that mean? Well, that means that the determinant is up to sign that expression. And so determinants are volumes, which this is a really nice fact. In fact, we will come back to this. This will get used later on in the course. So, how do we find the volume of a parallelepiped? The answer is, well, we figure out the vectors. So maybe I have the vectors, we'll make up numbers 2, 1, 3, 4, 5, -1, and 3, 0, and 2. Okay, so here we go. What do? First off, create a 3 by 3 matrix. So first row, first vector. Second row, second vector. Third row, the third vector. Now you might be saying, well, which vector should be the first one? And the answer is it doesn't really matter. You can pick them in any order. Now if you change the order of your choice, you might change the sign. But remember at the end we're going to take the absolute value. So it's okay for right now to not worry about it. So we're taking the determinant of this. So usually you use these straight lines to indicate determinant. So let's take the determinant. 2 times 5 times 2, that's 20. 1 minus 1 plus 3, because remember we wrap around, that would be negative 3. 3 times 4 times 0, because we wrap around, is 0. All right? And now, what's the other ones? 3 times 5 times 3. Well, that's 45. Subtract. All right? 0 times minus 1 times 2. That's 0. But remember, we're going this way. So it's not just 0. We subtract 0. And 2 times 4 times 1, 8. But again, because we went this way, and with wraparound, we subtract 8. All right. So let's see, we got 20 minus 3, then minus 45, minus 8. Well, It's really 20, that's really a positive term. And if you put these together, that's minus 56, meaning that we're going to get negative 36 as that determinant. Well, is that the answer? No. Because remember, a volume can't be negative. That's why you need these absolute value signs to correct. And so the volume is going to be equal to the absolute value of negative 36, which is positive 36, and there you go. Now, positive 36 what? Well, whatever units we're working on. We didn't give units here, so we'll just say 36 cubic units. And there you go. Now, the big takeaway here is later on in the course, we're going to talk a little bit about a volume of a three-dimensional box, a parallelepiped, and you just have to remember, oh, yeah, volumes are easy of boxes. It's this determinant. And then life is easy. Good.